Good morning, Michael.
Good morning, Matt.
What's with this title for the video?
Well, limitless is the important word here. We've been trying to develop calculus without ever saying the word limit. That's very much not the tradition in how calculus is typically taught. They typically talk about limits, this goes to that, this goes to that. And we want to get away from that because we think there's better ideas. We've been using this intuitive idea of approximation. And that's what we're going to make precise now, because at some point in calculus, you have to be precise about what you're talking about in order to do things exactly.
Well, let's start with a simple example, like a function, y equals 23x.
Okay, let's write that down, y equal 23x. Now, whenever we've been doing approximations, we've been talking about with something being small. So in this case, let's just take x to be small. If x is small, this function is close to what? I'll give you a hint, it's close to an integer.
I'll pick the integer to be 0.
That's right. Some people want to say, oh, there's 23 there, maybe it's close to 23, but it's not, it's close to 0. So it's approximately equal to 0 for x small. Can I say when x is small?
Yeah.
And when I say small, I just mean it's close to 0.
Yeah, so the key thing here is this piece.
That's the right piece. That's the right piece. Because if x was close to 100, this thing would not be close to 0, right?
Yeah.
But I think we understand intuitively this idea. If I give you a small number like 0.00001 multiplied by 23, it's pretty close to 0, right?
Well, yeah, you could see it from the graph, right?
You could see it from the graph, but that's such an easy graph. Maybe we can do a slightly more complicated example. How about something like this, the square root function of 16 plus x. Now, when x is small, what do you think this will be close to?
Well, if x is small, I'll pretend it doesn't exist.
Okay.
And I'll get the square root of 16, which is 4.
Right.
So a very rough approximation, but it gets better as x is small, if x is 0, as I said. So approximately equal to 4.
Very good.
Can we do better?
Can we do better? Well, see, we're using approximations, and this is where people say, oh, you're waving your hands and not being precise. So I can be precise. I can say this is not approximately equal to 4. What it's equal to is 4 plus a little error function, which I'll just call e of x. Okay? This is what I call my error function. And this is what we're using to make precise all these approximations we've been talking about in this series of videos. And the nice thing about this error function is we don't have to know it exactly, but we have to know two properties for it. First thing is if I stick in 0 here, what should
It's exact.
It's exact.
So e of 0
Is equal to
0.
0. And the second property is the approximation property, which is that when x is small, the error should be
Small.
So that's the second property. E of x is small when x is small. And that's the only thing we need to know about the error function. Now, this function here, okay, I could write out the algebra and I can tell you exactly what the error function is. It's kind of annoying.
Well, you could use binomial
You
theorem.
use binomial theorem. We could get it precisely, but let's skip the algebra. Let's just do a little graph here. So the square root function looks like this. Okay. And if I take the point 16 here, I get a point up here, which is the square root of 16, which is 4. And now if I move over by a little amount x, you can see this thing will change to here. And so maybe I can draw a straight line here, and the little difference between here and here is the error. That little gap
is
e of x.
Yeah, so as you move this point closer and closer, the gap gets smaller and smaller.
Smaller and smaller.
And so, like you say, when you're right at the point and there is no gap, but as you make x smaller, the gap gets smaller, so the error gets smaller.
Right.
And you can only do that if locally the function is smooth enough so you can monitor the gap well.
So you can monitor the gap. So this error function, it's got this property that it gets small as x gets small. And you're right, in this case, it's a pretty smooth function. You can actually write it down, and it's not too hard to look at. But I would like you to think about the error function as a function all by itself. Has these two properties. It hits 0 at 0. And then as x gets small, it has to go close to this thing. So it might look like that, might look like something nice and smooth. It could be jaggy like this,
but
it still
it'll
has to
be
come in there.
smooth itself. That's the
It
point.
could be smooth, not necessarily. It could be
Well, I
something
mean, it's
really.
not got a jump in it anywhere or a point.
It never jumps up really high. But you could have an error function like this, and actually this happens a lot in computing, where the errors are sort of because of round-off error. So your error function, it looks like little steps, but the steps always go down to 0. So error function doesn't have to be continuous, it doesn't have to be smooth, but it does have to have this property that as x gets small, the e of x gets small. That's the key property.
Well, what you're saying is very interesting because traditionally when you do calculus, we're assuming everything to be smooth
Yes.
as we do it in the first year class. But here actually we're expanding our region of explanation, if you like, by allowing things like this graph here.
Exactly. So we're giving a lot of flexibility by letting this error function be just about anything, except it has these two properties. E of 0 is 0, and e of x is small when x is small.
Great.
Now, this is a simple approximation. We can do higher order approximations, and perhaps I can actually do this here. So we would call this a 0th order approximation to this square root function, okay? What that means is we're getting a constant. A
Right.
first order approximation would be a linear approximation. And in that case, it turns out, I'm not going to do the calculation for you, but I can write this down. This is approximately equal to 1/8 x. And then there's an error term. But now the error term I express in this form, the error function multiplied by x.
How did you get an 8?
Well, I did a little calculation in my head.
I did this too. If you divide by 16 and pull it out, you get 4 in front, you get 1 plus x over 16, right? And then take a half of that.
Take a half of that. So what's going on is you're taking the derivative of the square root function, which gives you a little half.
So shouldn't,
And
but
then
aren't
there's
you
a 1
going
over the square
to, by binomial theorem, I get a different answer. So let's see if my answer makes any sense. And then we use the binomial theorem, so it's half of this. 4 plus 1 x over 16 times a half. And you're right. We
See?
agree. Totally different way of getting it, but good.
I'm a little bit concerned about this 1/2 here.
Because it's square root. 1 plus nx, n is a half.
See, but then I should have a 32 here.
No, we got the 4 in front.
Oh, you're right, you're right. 4 cancels, yes. Okay,
Perfect.
Matt, we had two different ways. Can I tell you
How
the
did you
honest
do-
answer? I plugged in x equal to 0.1, typed it in my calculator and thought, oh, it's approximately 1/8 of 0.1, which is a cheat. But okay, can I hide this?
Yeah,
little
yeah,
part?
now we can,
We agree on what the approximation is.
yeah, that was
But
fun.
what's different now is before we had just 4 plus an error term. Now we have 4 plus a linear part plus an error term times x. We will call this a first order approximation. Okay, so this is saying this is the best linear approximation that we can have for this function. And we're saying very precisely what the error term is. Again, if we plotted this very, very carefully, this error term, it's different than the one that we had here, but because there's this extra x here. But again, it will go to 0 as x goes to 0.
interestingly enough, we could continue this on, right? Like this could start out to be something of the order x, and then we're getting a term in x squared would be the next.
That's right. So this, maybe we'll erase a little bit so that we can add some little notes. This is what I would call a first order approximation. And then you could even go further. So there'd be 4 plus 1 over 8x plus there'll be an x squared term, and there'll be some coefficient here, which I don't know what it is. It'll be a.
Sure.
And I know it'll be negative.
Yes.
And then the error term will have an x squared multiplied by it. This is what I call a second order approximation.
Well, my guess would be this would be then of the order x, leading here would be x cubed.
That's right. So this error function will look roughly like x, or the absolute value of x, and then it's multiplied by x squared. So again, the point is that e of x goes to 0 at a certain speed, but then we have this extra factor of x squared making it go to 0 even faster.
So what's interesting is that if we go back to what we did earlier about derivatives, this is a linear term. This is a quadratic term.
Right.
And so we start to see linear, quadratic. It harkens back to what we did in an earlier video, the Taylor series.
Exactly.
So
So there's the Taylor series approximation to a function. So you can add more and more terms if the function is smooth enough, and you can get higher and higher order approximation. So I can go up to an x to the n here, for instance, and my error term would now have an x to the n multiplied by it.
So really, we have this hierarchy of continuities in terms of the smoothness of the function in order to be able to calculate those coefficients. In this case, it would be a.
Right. This encapsulates everything that we need to know to do calculus without limits. Now, for my mathematician friends who are watching, they'll say, well, can you say limit at least once? So I will say limits once, but only once. And the real property, the thing that e of x is hiding or replacing is this statement: the limit of e of x as x goes to 0 is equal to 0. That's the property that we're encapsulating in our error function.
But we're not really treating this whole process of limit as an object.
No, we're not thinking of this as an object. We're thinking of the error function as a way of putting a name on our approximation, precisely putting a name on the error of our approximation, and then we can work with that. So there's all sorts of interesting things about error functions, like if you have two error functions and you add them together, it's still an error function. If you take an error function multiplied by another error function, that's also an error function. If you take an error function and multiply it by 10 million, it's still an error function. Okay, bigger error, but it's still an error function. So all these properties that people try to teach you about limits, which can seem confusing at times, they just come out to properties of what error functions can do.
Fantastic. Good work, Michael.
Thank you, Matt.